Hello, and welcome to today's webinar, Integrating a Path to Digital Transformation. This is a joint webinar from Ricardo North America and the Digital Twin Consortium. My name is Chris Brockbank, and I'm Vice President of Technology and Strategy at Ricardo Inc., or Ricardo North America. As you will notice, that is not an American accent. I'm an import. I'm originally British, and have been over here in America working at Ricardo for 6 years now. My background, I started with Range Rover many years ago, more than I really want to count. I've worked at a startup transmission company before joining Ricardo, and I've worked at a number of Ricardo sites and locations around the planet. Today's topic is digital twin, a topic that is new, and it's actually defined in a variety of different ways by a variety of different people and companies. And that definition complexity is one of the topics that we will be touching on today, and is why Ron Zarvi from Microsoft, and also a member of the steering committee of the Digital Twin Consortium, is with us. So Ron, would you like to introduce yourself and just say a little bit about how you've ended up getting into this wonderful world of digital twin?
Great, thank you. So I'm Ron with Microsoft. I'm part of the Azure IoT product team, and I lead our strategy for involvement in various standards and consortia, and I represent Microsoft in several such organizations. I've been involved with standards throughout my long career. I've also done strategy consulting, and I started as an electrical engineer, so I like to tinker with IoT devices as part of the fun. So I'm in a position today that allows me to pull all these three things together, so it's very gratifying. Microsoft has a digital twin platform offering as part of the IoT overall offering. And today I'll speak about the new Digital Twin Consortium that we're part of, and it'll include that in part of this presentation.
Thank you, Ron. And we also have today Madison White, also from Ricardo North America. Hi, Madison. Would you like to say hello, introduce yourself?
Yeah, hey, Chris. My name is Madison White. I'm part of the technology and strategy team at Ricardo North America. My responsibilities is driving strategy for software solutions in the connected, automated, and autonomous driving space. Prior to Ricardo, I had a product development role at Wind River Systems. So I'm really bringing the experience of driving software solutions and connectivity, like over-the-air updates, standardized frameworks, and bringing that to Ricardo, as well as leveraging the experience in connectivity and vehicle data collection to the topic and innovation within digital twins. I also represent Ricardo in the Digital Twin Consortium, so I'll be working with Ron and other members of the steering committee, as well as the other working groups, to really drive this innovation forward.
Thank you, Madison. And I think you told me you're now sitting on so many of those committees, you're struggling to get the rest of your work done. So I'm sorry for giving you too much to do.
No problem. We'll get it done.
Thanks. So today we will start with a quick overview of Ricardo, for those of you who don't know us too well, and then a look at the technology trends and market drivers before starting to dive deeper into digital twin and digital twins in automotive. And then Ron will discuss the Digital Twin Consortium in more detail and how we can help to go forward with the digital twin world. We'll then have time at the end to go through your questions and give you some answers. And please, as we go through this, please send in those questions. We'll go through as many as we can with the time given, and any we don't get around to, we will respond to after the event. And also for people watching this on catch-up or on video after the event, please also send in your questions and we will get to those as well. Thank you. Ricardo is a global engineering and environmental consultancy. We specialize in transport, energy, and scarce natural resources. There's a century-long record of delivering projects that are rich in innovation and technology, and our work extends across a range of market sectors. Working at Ricardo is never monotonous and never boring. As an engineer, you could be working on passenger cars or commercial vehicles, and then on rail or defense, motorsport, motorcycles, power generation, and green technology that's emerging across the world. In the era of advanced electronics and software-driven vehicles and the proliferation of connectivity, we're bringing our experience from vehicle expertise and embedded software, data activation, and automated and autonomous systems integration. And that's what we'll be going through today. But across everything we do, we remain committed to the ethos of our founder, Sir Harry Ricardo. Sir Harry was the most innovative mechanical engineers of his time. And in 1915, he set out on a mission to maximize efficiency and eliminate waste in everything he does. And that's what we do today. Our vision, therefore, is to create a world fit for the future. We do that across market sector, working with industry, governments, and geographically all over the world with over 3,000 engineers, scientists, and technical support staff. You see 6 main topics listed around the side of this picture. And today we're focusing on that top right, connectivity and intelligent devices. And here in Ricardo, North America, we support that vision by having our mantra to integrate a path to a better mobility future. We build that on a number of pillars: advanced propulsion systems, software and controls, thermal management, until we get to where we want to be of a zero carbon mobility. Vehicles are becoming increasingly connected and moving towards high levels of autonomy, and the vehicle is becoming increasingly software driven and complex. In 2017, Ford stated that the F-150 had 150 million lines of code. In 2019, JLR stated that a self-driving car will need 1 billion lines of code. Look, I'm sure people know, but it's a well-known figure that the F-35 fighter has 24 million lines. That just shows how complicated and complex the cars are coming. And we're now going to move into highly automated driving, vehicle to X, V2X, Internet of Things, high performance computing, and then consolidation of how to do that. It's all about connectivity in the data. To be a partner to our customers, Ricardo is focused on 3 key areas in that connected, autonomous, and automated vehicle space. Autonomous system solutions, both in software and hardware, and they need to come together. Advanced electrified embedded architectures, with a focus on the benefits and the advancement afforded by platform architectures. And connectivity solutions, data activation, and that leads to the digital twin technologies. And that's why today's webinar focused specifically on the definition of and advancement within that digital twin space. Number 1, technology trends, innovations, and challenges. Number 2, definition and dream state for digital twin technologies in automotive. And finally, 3, the role the Digital Twin Consortium and Ricardo will play in accelerating the advancement and adoption of digital twin technology from early adoption to scale. So with that, I'd now like to hand over to Madison to take us through the technology in more detail.
Thanks, Chris. So right now I'm going to dive into technology trends and market drivers in the area of connectivity, automation, and autonomy. So starting from the evolution of the vehicle from being a completely unconnected system to an intelligently connected system of systems. If we move from the unconnected vehicle to embedded connectivity, the industry has incorporated systems like GPS, GM's OnStar, Ford Sync. The car has become connected to the cloud. Beyond that, we saw this innovation in mobile phone technology and the connection to the vehicle. So broadened technology, infotainment, and streaming. And what this has done to the industry is enable the consumer and the mobile phone to actually define the vehicle experience. So consumers are expecting the vehicle operation and the experience within the vehicle to be very similar to their mobile phone. Moving forward, the car is not only connected to the cloud any longer, but it's smarter. So there's intelligent analytics, there's machine learning, AI going on in the background. So it's not just connectivity, but it's smart, intelligent connectivity. And then on the way to this era of mobility where the vehicle is one system of systems and one means of connected transportation, the vehicle is now connected to not just mobile phones, but to other vehicles, to infrastructure. So it's intelligent, highly automated, moving towards autonomous system that's communicating, connected to vehicles, infrastructure that can be inherently and remotely updatable. So we have this kind of two-way connectivity pipe. We can deliver new services there's a whole shift in the supply chain, not just in technology itself, but driver expectations, as well as the way the OEMs are interacting with the software suppliers. There's a kind of overhaul of the definition of the value within the vehicle. The evolution of the vehicle and vehicle technology is heavily driven by innovation in software. So the value of the vehicle is being driven primarily by software as we move forward rather than hardware-driven value. We see convergence in the areas of connectivity, automation and autonomy, electrification, and all the way through to mobility. And the key here, it's not just a software evolution or software convergence, but it's an evolution of the owner, operator, and the usage and expectations of the vehicle itself, and a whole evolution of the supply chain and how components of software solutions, mechanical and hardware solutions need to come together through this evolution. All right, so in order to realize the benefits of this software technology convergence, there must be an evolution across a broad spectrum of technologies, from connectivity and connectivity availability, data frequency and fidelity, simulation modeling, and an overhaul of existing processes and culture. Now, if we look at connectivity availability, this varies on the vehicle type and vehicle use case. So for passenger car, there's a proliferation of connectivity in production vehicles, even first or second generations of remote software update deployments. But if we compare that to commercial fleets or heavy machinery and agriculture, where the vehicle might be in a far remote location, there's sparse connectivity availability. So vehicles need to be consistently and always connected for realizing the true benefits of connectivity advancements. Beyond that, we have data frequency and fidelity. So the impact of not having real-time data impacts the accuracy of the data that we are informing our modeling and simulations. Beyond that, there's a discrepancy in the quality and the accuracy of the data that we collect. So we need higher fidelity, higher frequency data collected. If we look at simulation and modeling, there are several simulation and modeling tools to date, but they're not currently informed by real-time data. So it's all coming together, right? You see connectivity availability, data frequency, and that's impacting our simulation and modeling. And finally, it's an advancement in processes and culture. So it's combining hybrid development methodologies, waterfall and agile development, incorporating these ideas of continuous integration, continuous delivery, and continuous deployment so that we're accelerating time to market for new features, new functionality, and a DevOps culture of continuous innovation and accelerated delivery to market. Now we're going to transition into the definition of a digital twin, the benefits of the digital twin, and its application to the automotive and transportation sector. Before jumping into digital twins, we'd like to focus on the benefits and capabilities around data collection, insights, and machine learning. And the Ricardo view and what we've been focusing on is looking at combinations of correlated component or sensor data, which can be indicative of faulty designs or future failures, which when you look at data from a single component, you might not lead to the same conclusion. So our projects are focused on training AI engines to intelligently identify these targeted data sets across aggregated vehicle data. This is development data as well as production vehicle data. And through this analysis and targeted data collection, we are able to identify faults, so future engine or mechanical failures. And with that, we're able to do predictive analytics. We're able to reduce the number of unpredicted failures, as well as reduce the number of unnecessary service visits. So it's really reducing the downtime of your passenger cars or commercial fleets, as well as reducing the amount of service visits and overall reducing the cost of operation and maintenance of your vehicles in production today. Now, if you couple the ideas of analytics and machine learning with this concept of shifting left is doing as much testing, validation, and development in a virtual environment as possible. So you're eliminating the number of physical builds that you have to do. You're eliminating the number of test miles that those physical cars have to run. And you're really leveraging the virtual environment for as much development, testing, and enhancements and improvements as you can before you actually have to do a physical build. So in the end, you reduce the cost and time to market for new features and services because you can more quickly and efficiently test these new features. These models must be informed by real-time data analytics, as we've already mentioned. So if you couple analytics and machine learning and targeted data collection, you can really harness the benefit of a virtual test environment. And the end goal is really to deploy new features, new services faster and at a more cost-efficient and time-efficient rate.
So Madison, that's really interesting. What do you think that does to the time to get a product from design through to manufacture?
Yeah, that's a really good question, Chris, because one of the main benefits of simulation, shifting left, and even the digital twin is the reduction of time to market for new features and services. So when you do as much as possible in a simulated or virtual environment, you could essentially be eliminating weeks, months, if not years from your development and production cycle. If you look at it from a software development perspective, acquiring hardware for new platform development could take months, if not a year, depending on the availability of a hardware. So when you start your development tests and validation in a virtual environment, you're light years ahead of where you would be if you had to wait for that hardware to be available. If you think about this from a engine design or whole vehicle build, the amount of time that it would take to actually build the engine, build the systems interacting with that engine in the entire vehicle, and then driving it the thousands of miles, you can do that all in a simulated environment to reduce the amount of time for development, testing new features and services, and even testing new benefits to that vehicle. So it's really focusing on reduced development time, reducing the cost to build and test those new services and functions, and getting new features out to the consumers as quickly and cost efficiently as possible. And that's a great transition into the next topic, which is the definition of a digital twin. Now, our view is data collection, AI, machine learning, it's only going to get you so far. And one of the major advancements leveraging connectivity and data analytics is the concept of a digital twin. And the digital twin is truly a virtual version of something that's physical. And what differentiates a digital twin between a simulation or a model is that it's in real time, or should be real time, informed with real-time usage and component status data. So as a vehicle owner drives its vehicle, as it moves around through harsh conditions, and as there is actual wear and tear, the virtual version or the digital twin of that vehicle or every component within the car is informed and impacted by that same data. The digital twin can be applied to every phase within the vehicle life cycle, from design development, test and validation, manufacturing, all the way through the operation and maintenance of this car through end of life. Now, the long-term vision of the digital twin in automotive is to have every single component within the car having a simulated version or the digital twin. Every one of those components interacts with each other, and that interaction and communication must be modeled as well. So the entire vehicle system has a sister or a digital twin version of it that is consistently informed with real-time data, real-time usage data. And if you couple that with smart sensing or adding new sensing sensor capability on the vehicles themselves, we can enhance the quality of data, the fidelity of data that's collected to best inform the digital twin. So it's truly a virtual version of something that's happening in a physical capacity. So when combining this idea of analytics, AI, combining digital twin, so we now have every single component within the vehicle has a digital twin. All of the interactions and communications are modeled as well and informed by real-time data. We really need to couple this with the right technologies, tools, and processes to realize the benefit of a digital twin. So first, focusing on hybrid development methodologies. The realization of a digital twin will be a coupling of software innovation as well as hardware. And it will be applied to safety critical systems, not just infotainment or telematics. So we really need to couple the ideas and methodologies of waterfall development, which are specialized for safety critical projects, and agile development methodologies, which enable quick learnings, accelerated delivery, and more efficient development and delivery of new features and services. Now, when you couple that with continuous integration and continuous delivery, as well as continuous deployment, the digital twin really encompasses this idea of a baseline which should be consistently updated. It reflects what's happening in the real world, but it's also an area which can test new functions, new services at a more quick and cost-efficient manner. And then coupling that with processes and the culture of DevOps, it's really shortening development life cycles, accelerated delivery, faster time to market at a reduced cost and reduced time. Now, coupling all of the technologies, the processes, the culture that we've already talked about, the digital twin can really be this continuous feedback loop, which enables enhancements in the entire life cycle of the car, from design development all the way through end of life. The way we view the digital twin is it could potentially benefit next generation concepts for any component within the car, the entire vehicle, whether it be commercial fleet, passenger car, heavy machinery, or agriculture use case. This feedback loop, we can consider it a form of continuous engineering, because as we're pulling real-time data from a car or any component within the car, the digital twin is being informed, and we can do predictive analytics and insights, and we can improve the designs for features that will be deployed through a software update or future designs. We've already mentioned the benefits of enabling virtual testing and development, doing everything virtually and shifting left as much as possible, but the digital twin really enables faster time to market and decreased cost. By leveraging the twin, instead of doing physical builds or doing the actual test miles of a vehicle, you leverage the digital twin for that perspective. And finally, we can enable benefits all the way through operation and maintenance, ownership change, and end of life through predictive maintenance, preventative maintenance, and predictive analytics, and making sure that our digital twins are dynamic, they're consistently informed with hopefully real-time data, they are predictive, they are dynamic, and they are truly a reflection of what's going on at the vehicle at any point in time. So digital twins are not a new concept, nor are connectivity advancements and simulation and modeling tools. However, there are a lack of connections between the physical reality of the component and the twin itself, which leads to development teams focusing on physical testing versus virtual and simulated testing environments. Beyond that, deployments today are heavy investments up front, and our customers aren't seeing the overall efficiency gains and cost reductions that they expected. And in terms of insights and performance enhancements gained to the digital twins today are not properly informed with real-time data. And when you couple that with varying data accessibility and connectivity availability, the existing systems fail to account for severity of use with changing environmental conditions. At this point, I'm going to be transitioning to Ron Zahavi from Microsoft and part of the steering committee of Digital Twin Consortium to address how the Digital Twin Consortium is addressing the challenges within digital twin technology and how we're working to overcome those challenges.
Thank you, Madison. If we look at these challenges and expand them to the entire industry, we can observe that there are several market challenges that need to be addressed. The main ones are limited interoperability, market confusion as to what a digital twin is, and the fact that digital twins can require a large investment, which makes it much more difficult to start with and be successful. So when we look at each of these areas, when we look at integration, there are challenges at several levels. One is between the digital twin and the existing equipment. How do you connect them? Another is between digital twins of different vendors. For example, between different vehicles, there will be different digital twins, and there's no clear standards to enable that. Another is the integration between different components of a digital twin. Some could be very different types of models. For example, fluid models versus airflow models. We are early in the digital twin market, and it is further slowed down by market confusion as to what a digital twin actually is. Everybody has their own favorite description for a digital twin and what it is and what the product life cycle is. For example, if you start with planning and then go through design, building, and operating something like a vehicle. It is causing confusion. For many, it isn't clear where to start, and we know from IoT that starting in the wrong place can make it more difficult to capture return on investment. And then finally, digital twin projects require investment and a lot of resources. There is a skills gap. We also know that digital twins control real things. There can be implications on things like safety and safe operations. So we realized that to address these, we need some sort of an organization. So how does a consortium help solve these types of challenges? We created recently the Digital Twin Consortium as this organization to address these issues and challenges. The vision is to be the authority on digital twins, to bring together academia, government, and industry in an open environment to address standards gaps, develop open source, develop an ecosystem to be able to advance innovation in digital twins. That's the main focus. To address the three main challenges, we need to improve the interoperability, we need to accelerate the market to mature it, and clearly explain and demonstrate the value of digital twins. We're addressing the interoperability challenge by creating things like reference implementations, looking at the different ontologies that exist out there, looking at security, looking at standards, identifying the gaps, and then we'll be able to work with different standards organizations to address those gaps. To accelerate the market, we're capturing use cases in different and related industries. We're looking at defining what a digital twin is, looking at the life cycle components, and coming up with baseline definitions that can be used by everyone. And to demonstrate the value, we're all capturing the skills that are needed, focusing on quantifying outcomes to demonstrate the value, and creating industry events to showcase and share all the information that we're collecting and learning at the Digital Twin Consortium. So to start, we've created several working groups. Some are horizontally focused and some are industry driven. The first group is one called Taxonomy, Terminology, and Technology. It also has a security subgroup, and it is focusing on defining the digital twin, exploring architecture of digital twins and different types of technology. The marketing group is also horizontally focused, and it's focusing on the messaging of the organization and the events that we're going to hold. And then to start with, we have several industry types of groups, manufacturing working group, an aerospace and defense group, and a couple of umbrella groups. So the infrastructure umbrella group includes things like smart cities, smart spaces, transportation, bridges, and so forth. A natural resources group is also an umbrella group that includes oil and gas, mining, energy, and utilities. Each of these may break into its own vertical later on, but we wanted to make sure that members will lead these areas, and we will add more verticals as we grow. First, they wanted to understand how some of these areas relate to each other and if there's commonality before we start looking at some of the differences. The organization has grown very fast. We announced it on May 18th with 4 founders and 14 groundbreaker members. These are initial members that joined the organization early. Anyone joining until the end of May was recognized as a groundbreaker. By the end of the first week, we already had 40 members. And today we're happy to announce we're closing on 100 members who cover the entire world region and different areas. And GE just joined us as another founder. At this point, Madison will continue the presentation and discuss how Ricardo is advancing the work at the Digital Twin Consortium. Thank you.
So thanks, Ron. In the next section, we're going to be focusing on how Ricardo is contributing to and accelerating digital twin technology within the Digital Twin Consortium, as well as our solutions and expertise in this area. So Ricardo actually joined the Digital Twin Consortium at the end of March as one of the groundbreakers. So one of the early members contributing to and helping accelerate innovation within this space. Our goal is to bring our century-long expertise in vehicle system to the digital twin technology. The Digital Twin Consortium is focusing on 3 key areas to accelerate time to market, improve interoperability between digital twin technologies, as well as demonstrating the value of the digital twin to the market. So our focus here is on automotive and transportation. So what we'll be doing is not only interacting with, working with, and contributing to the consortium, but leveraging learnings and best practices, as well as standards that are brought out of and agreed upon in the consortium to our projects and to our customers. So in terms of improving interoperability, We will be leveraging the standards, best practices, as well as focusing on our own integration capability in the area of digital twin, and contributing baseline models in the area of transportation and the vehicle itself for digital twin reference implementations. We will be accelerating time to market by focusing our data collection strategies. So really improving how data is collected from the vehicle, what frequency, what fidelity, how it's stored, cleansed, etc., so that we can best inform the digital twin, and really bringing the digital twin technology, applications and benefits retrospectively into our past projects, current projects, and future projects. So integrating this capability to improve our customers' bottom line as well. So demonstrating the value of reduced cost of ownership, reduced downtime, and enabling accelerated delivery of new features, new designs at a faster and more cost-efficient pace. In terms of our capability in this area, Ricardo has a broad range of expertise and past project experience, ranging from data collection and insights, modeling and simulation solutions and products, and really leveraging our vehicle system expertise. One division within Ricardo is called Ricardo Software, which has a broad portfolio of simulation and modeling tools, which when advanced are informed with real-time data collection. This is our delivery of digital twins to the market from a product perspective. When you couple that with our military-grade solution for targeted data collection, we enable targeted data collection for enhancements in the area of predictive maintenance and predictive analytics. We have over 20 years of diagnostics, development, and data collection experience. And we're coupling that with a team of data scientists, so focusing on data analytics and machine learning to do fault prediction, fault detection, so really enabling our customers to know when their vehicles will fail at a future period of time, predictively and proactively resolve those issues when leveraging digital twin type technology and bringing our expertise in the vehicle to all of these functional areas. So we understand how the vehicle is built, what types of data can tell us when a failure is going to occur, and we really understand how to resolve those potential failures moving forward. Now, one key that we've touched on multiple times here is the concept of real-time data collection and activation, if you will. We view this data activation pipeline as one of the key areas of innovation that needs to be harnessed to really realize the benefit of a digital twin. And Ricardo can provide value and is providing value in past and current projects across this entire pipeline with targeted data collection strategies. So knowing what data needs to be collected and when, where this data needs to be stored, where it should be cleansed and analyzed, really what the data is telling us, so we know how the vehicle can fail. We know when it's doing well or what any wear and tear of any component within the vehicle or multiple components is telling us. We have past product experience and really a lot of expertise in the solutions. So if something is going wrong in the vehicle, we know how to fix it, and we know when the vehicle is telling you something is going to be going wrong in the future. And it's not just from the mechanical space, it's from the software space as well. So we have end-to-end experience and expertise in the area of over-the-air updates. So when there's something going wrong with your software platform, we know how new software, new services, and enhancements can and should be deployed to production vehicles. And the idea here is to really capitalize on this data activation pipeline to best inform your digital twin to realize the benefits across the entire product lifecycle, from product development, so design, test, validation, through the manufacturing and operation of your vehicle, through end of life. So that concludes our presentation portion of the webinar, and I'll hand it back to Chris for question and answer.
Thank you. Sorry, I went a bit quiet then for a second. So thank you, Madison. Thank you, Ron. We're now going to move over to the questions, and the questions have started flying in. I just want to start by asking, one of the questions came in, and I'm just going to ask if the person who sent it in could expand upon it. It said, is there value for the digital twin use case in engine design having actual 3D models rendered? Could you just, whoever sent it in, I haven't got your name, I'm sorry, just send in a little bit more on that one so I can understand. Are you talking about virtual reality? Are you talking about whatever? Just we'll just hold that one for now. Okay, let's have a look at some of these questions. So Madison, one for you. Have you seen digital twin technology adopted by customers to date?
To date, yes. One of the topics we covered today is kind of the confusion around what digital twin means. So first, what we found is our customers all have a different definition and understanding of digital twin. So this could be even on the far end of the spectrum, from over-the-air software updates to a really robust implementation of digital twins. So we've seen a digital twin from product development and design, digital twin of a manufacturing plant. So not only the way parts move, but the way people move and the way people and parts interact with robots, and all the way to predictive maintenance and predictive analytics. So it's really a broad spectrum of implementations, technologies, and really an understanding of what digital twin means and how it can be applied.
Okay, I mean, yes, it's interesting. I saw on Automotive News today that Volkswagen announced the name of their new head of software. This just shows how the industry is changing. You'd normally expect a car company to announce their head of engines or their head of vehicles, but they're now announcing their head of software. So just going back to that question, though, and I'm going to send this over to you, Ron. If you can just go over again about what the benefits of joining the Digital Twin Consortium are.
Sure. Obviously, there's several areas such as being able to influence. So if you join something like the Digital Twin Consortium, you can participate in the working groups. You can chair the working groups, and you can provide, if you're more of an end user, you can provide requirements that can then be addressed by the members and doing the work. So one thing is to drive really the need and what it is that from technology that you would like vendors to provide. And other areas, collaboration and thought leadership. So collaborating with peers, being able to share research and development together. And there's things like speaker bureau that you get speaking opportunities and visibility for the company that you represent. And that's also from a marketing perspective. So basically being listed in the directories, being able to present at the different conferences and events and getting industry recognition, and then being able to get things like the badges that you've seen being groundbreakers and getting recognition like that as well. So basically there's influencing capability and advancing the innovation, there's collaboration and thought leadership, and there's marketing aspects as well.
Okay, yeah, we are very proud to be a groundbreaker on that, so thank you. Questions coming just for both of you to follow up to that. So start with you, Ron, and then maybe Madison can add in. So it says, the question is, although the Digital Twin Consortium is still young, it's in infancy, can you share something you've learned so far from all these working groups?
Yeah, sure, I'll go first, thank you. For example, we have seen that an advancement already of the fact that everybody had, and we knew this, everybody had different definitions for the life cycle. So I mentioned earlier that you could have, a product life cycle may be the design, the engineering, the development of it, and the production. But when everybody started thinking about that, some had views that it starts in procurement and it goes all the way to retirement of the product. So we immediately saw a great contribution to the terminology, the life cycle of the product, and now everybody's starting to look at the use cases within that life cycle. And another interesting area is the overlap between certain domains, and then the fact that there are some things that cross over, and then some things that may be more unique for each domain. So those two areas we sort of saw within the first few weeks of the meetings. Madison, what do you think?
Yeah, I would agree. I've participated in all of the working groups so far. And what's interesting when you look at the natural resources and then maybe the aerospace and defense group There's a focus on projects in oil, mining, natural resources, and then in aerospace and defense, it's more of a product or component perspective or something more similar to a vehicle. So we really have to have digital twins for every component within a specific product, but also kind of how those products interact with a larger system. And then in a larger overall project, the project has to have a twin itself, so you can track phases across development of much larger infrastructure pieces. So it's really interesting how narrow focused the twin can be, but how broad it can be as well.
That's really a good answer. It segues into the next question that's come from Jason. Jason has asked, with the large amount of investment still required to address the current gaps in the ideal digital twin technology, what does the panel see as a stepping stone technology to get there? Who wants to take that one?
I'll go first, and then I'm sure Ron can chime in. So first, if we look at it purely from a transportation automotive perspective, because we can take this very broadly, every component within the vehicle needs to have a model or a twin, right? All of those models need to be dynamic and they need to be able to be updatable. Beyond that, all of those models need to communicate with each other, and that communication needs to be done in a standardized method. So that standard needs to be created. The security mechanisms for how those things are built and how they communicate and how the data is coming into informing those models, that security standard needs to be defined. And then more broadly, we need to have really targeted data collection strategies and understanding what data is critical for informing a twin. So when we're talking to customers, most customers have their own definition of what and how data is collected and really how they're analyzing it and what they're doing to enhance products. So it's really understanding of the value, what's needed to inform digital twin, what models need to be created, and the standard mechanism between how those twins communicate together. And I mean, that's a lot of what the consortium is doing, right?
Yes, absolutely. I was going to go actually in the same direction as well. I think what's really important, given the development of the definition of all the different components that make up a twin, and I think I mentioned some of them. It's all the way from simulation to other types of models, geographical models and geological models, and fluid and aerodynamics, and all these things. They all have to communicate. So I think the interim sort of a mid-step is to be able to understand the APIs, the interfaces between all of these and how they exchange data in the data format, and then sort of a definition language for defining digital twins and the semantics so they can actually interoperate and share in that information. So once we have that, I think there'll be a lot of flexibility for different vendors to provide their value added with different components that perform certain functions. As was mentioned, security is another one. There's some members in the consortium looking at defining what a secure twin or a component of a digital twin that needs to look at security and what that means, simulation and other areas. So all these, once you know how to exchange the information in a consistent way, there'll be a lot of innovation of how to build these things together.
Okay. Okay, thank you. Okay, so Christoph has now come back against that first question we had. The question was, is there value in the digital twin case in, say, engine design of having actual 3D models? And he's talking about visualizing dynamic behavior in like a virtual reality style of something that we do. What's your vision, Madison? Do you think that these digital twins will just come up with a data stream at the end that says, hey, here is the damage that was done, here is the stresses that are being used, here is, or do you think it would actually, are we going to get to a point where you could be seeing in a, say, almost like, you know, a virtual reality world and seeing the entire vehicle and seeing every operation and seeing everything inside the engine? We use that a lot on design when we're designing in the 3D in the virtual reality world. We can take slices through engines and transmissions. We can move things around. We can pretend to take them apart, see how easy to get to. But from an actual dynamic response, do you think that would be a good output?
I think that's the direction that the industry will be going into. Yes. So if we're if the intent of the question is to say, is it beneficial to couple a digital twin with some sort of virtual reality? I think the answer is definitely yes, because you can visualize the way fluid dynamics, heat, or anything that's happening to the vehicle is actually impacting the twin. You can not only do that through real-time data, but you can do that through simulation as well. So the twins should be a combination of data that's coming from an actual physical component, as well as simulating or predicting future usage, so that we can best inform new designs, new features, and design our engine or any component within the vehicle to be better, longer lasting throughout its entire life cycle. And then if you just look at virtual reality and coupling design and digital twin in this era of COVID, it would be an even greater benefit to have people in remote locations being able to leverage artificial reality tools to co-design, to cooperate, to collaborate in remote locations. So all across the board, yes. Okay,
if I may add, I think the topic you raised, the whole mixed reality twin, if you will, is a very exciting area, because it starts to blur the lines between the physical and the twin, because you've got an area where they're both coexisting in a sense, spatially. And then you're able to interact with the physical world and with the twin, either separately or together, where the twin may or may not control some of the aspects of that same space. So looking at those engines and 3D simulations and all that, I think you'll have part reality, parts of the simulations, and be able to mix them all together in the same space. It's a very interesting area.
Yeah.
The smile on your face there, Ron, is just shows the enthusiasm you have.
Yeah.
Okay, I've got a couple more questions coming. I want to try and maybe add them together. I'm sorry, I'm zipping between screens here. How do you rectify moving left with the vast need for real-world data that is needed to create those robust digital twins?
Yeah, that's a good question.
Split that question up.
Yeah, so first, the digital twin has applications across, we've already touched on this, through an entire life cycle of the product, right? From the design phase, where if this is a brand new component, there is no real-time, real-world production data, right? So the key is really focusing on dynamic and updatable twin. So the twin has to evolve as the design of the physical component evolves as well. So, I mean, that's kind of rectifying, because you can't shift left with something that doesn't exist. You can inform the virtual model of something that's, a brand new concept. But say you have a twin of an existing engine or existing physical component, and you're designing a next generation engine or a next generation software platform, that future twin will be enabled from real-time data from the existing production deployments. So it's a combination of how the twin is applied, what aspect of the life cycle the twin is applied to, and then, when possible, inform the data with real-time usage and application data. And Ron, if you have anything else to add there.
No, I think that makes sense.
So Jeff has asked a question that's related to that. He said, what's the plan to address the time lag and computing power requirement for traditional 3D simulation to keep up with the real-time data input?
Yeah, that's a good question. So it's a difficult one to answer, because it's asking something that's very future-oriented, and the compute power needs to evolve not only in the vehicle itself, because there should be some processing that's happening on the car. And we see that compute evolution happening from, these electrified ECU architectures, from one function, one compute, to this domain architecture, to this kind of fluid compute, where compute within the car is on any ECU, it functions as a service, or it can be offboard as well. The compute needs to be advanced in this fog location as well, so that we can minimize the time or the distance between the cloud and the car. And then we really need to understand what types of data is going to be coming off of these future-oriented digital twins, and how our cloud platforms, our analytics platforms, need to adjust to really harness the data that's coming off any twin. I think, Ron, you might have an input as well.
Yeah, no, it's whether it's a vehicle or other similar structures that can produce a huge amount of data. It's really going to be each item can have a twin, and it's all going to be scenario and use driven. So obviously there are some things that need to be analyzed immediately, and you need to be able to run that at the edge, and you need that computer power at the edge and the visualization potentially there. And then there's some scenarios where large amounts of data need to be transmitted back for further analysis, or it's a twin that's a larger twin that needs to run maybe weekly or monthly and analyzing different aspects, and that you might need a cloud computing infrastructure for that, and then you collect that data when the car reconnects. There's obviously aspects of car driving and operations that it's going to be in areas where you may not have connectivity. So you need, whether it's safety or other traffic, I think the twin is just another aspect of all those scenarios that you need certain power at the edge versus other areas. And we need to understand, I think through something like this consortium, we need to understand the use cases and the needs and the amount of data to figure out the storage and the compute required for each type.
So, yeah, and just one other add here is the question first starts with the time lag between data coming off the car. And Ronnie pointed out that there will be scenarios where there is no capability for real-time data collection if this vehicle is in some remote location, right? So one of the things that we found through conversations with our customers is to optimize the way the vehicle is collected off the vehicles, and also make sure that you are understanding what data that you need, so you're requesting or pulling for really targeted data sets. Sorry, Chris, I cut you off.
No, I think you've just answered my next question, which is, are we therefore going to be held back by needing lots of onboard memory for storage, onboard storage, or needing 5G, or is that going to hold us back in the path to this digital twin world?
Well, the 5G is coming to market now, right, and moving forward. So I wouldn't say holding back. I would say those advancements are going to be accelerating the rate at which digital twin technology will come to market. And then we know that the compute power within the vehicle is not only becoming consolidated, but it's becoming more high performant. And with this idea of service-oriented architecture enabling compute and just the functions within the car to be onboard and offboard kind of simultaneously, I think that will also help the data to come off the vehicle in a more quick and cost-efficient manner, leveraging that high-performance compute.
Yeah, I think that where we are in the market, how early it is, that some of these things like compute and storage are not going to be the main issues that take time. I think working out some of these other things and starting now to get ready for the market as it grows and accelerating it, looking at that interoperability issue and things like that are going to be things that can actually take longer. But I think that they'll develop together, and one will address the other by the time it's needed.
Okay. So Ron, another question's coming for you. Will you add other vertical industry groups to the Digital Twin Consortium?
Yes, so we started the consortium. Obviously, it's member-driven, so the steering committee did not want to create many different verticals. We realized that it will be depending on the interest of the members, so we created the first 4 that we listed, and again, some umbrellas to combine them and allow them to break off as there is more members joining and specific interests. So we can imagine, as many as 20, 30, 40 such verticals, but it will be done over time. But basically, members joined. The security group, as an example, was something that was created by members that have joined and immediately wanted to work on security. So as members suggest these, they write the charter for them, and then the steering committee approves new groups as needed.
Okay, we've got literally 1 minute left of questions, and for you, Madison, without maybe going into too much detail, can you give an example of real customer project where Ricardo's data collection analytical AI engines have been applied and customer outcomes? So within the bounds of confidentiality, you've got about 1 minute to answer that one.
Okay, definitely. So think we touched on coupling real-time data analytics or aggregating data collected over both production fleets and development data that we can leverage AI engines to effectively and predictively target these sensor data components for predicting future faults. So we've had several projects actually where we've worked with OEMs not only across their development vehicles, but collecting their production vehicle data to help them decide how to collect the data, what data needs to be collected. And we've, I guess I can reference 3 projects without naming customer names. We enhanced the data collection at the service bay because there were failures occurring. The OEM didn't understand why. We did analysis, we understand what caused the failures, what data needed to be collected and at what point. So we basically removed that failure from occurring because they enabled proactive maintenance. In another example, we have a project where we reduced the number of unpredicted failures by 70% and the number of unnecessary service visits by 40% by training an AI engine to detect future faults. So those are 2 good examples.
Okay, thank you. So I'm just going to thank Ron and Madison for your time. I also would like to thank everyone who sent in questions. Please carry on sending any questions. Anything we haven't got to, there are some we haven't got to, we will answer them and we'll continue doing so. And anyone who's watching this on catch up, please also send in questions and we will get to that as well. In the last couple of minutes, just want to mention the next webinars that are coming up. July 29th, we have Future Truck for North American commercial vehicles, with a focus there on the requirements for and the powertrain architectures to deliver the future truck requirements. And then August 5th, we will go on to a zero emissions with hydrogen fuel cells. This is carrying on from our first webinar on the fuel cell and as part of the fuel cell series. And we're looking at transforming power across market sectors. Use of the fuel cell, not just in transportation, but also in things like with Ron and Microsoft, stationary power applications for servers and areas to be using fuel cells in those areas. Beyond that, there will be more coming. Any questions, please email me. The names are on the screen to myself, Madison, or Ron. And so last time, Ron, Madison, thank you very much for your time. Thank you for your contribution.
Yep, thank you for having us.
Thank everyone sending in the questions. Thank you very much.
Yeah, thank you for